Okay, Aaron, it's all yours. You can do an introduction, tell us what you lab or whatever. And also, before we get started, do you want us to ask questions throughout, or do you want us to save them to the end?
I think we can ask like throughout the ask a question whenever you have them, and I'll be able to talk with this.
Okay, and then, sorry, do you want to circulate the Google Doc to all of us with notes for the talk? We also crowdsource note taking for all the speakers.
Yeah. I think maybe the students it was working great in the first first class, and then it kind of became silent. Okay, cool. So so first of all, thank you for having me. I think you all do like really interesting and relevant things, and a lot of the things that are kind of intersecting with things that I'm interested in. So my plan was to do some kind of overview of the different kind of projects and ideas and things that I'm interested in and that I was working on, and then focus on one direction. So 2 or 3 papers that were in the main section. But feel free to, so the first one is going to be very broad and introductory. If you want to kind of talk more about these ideas, so I'm from the University of Haifa. I did my postdoc in London a while ago with Bahadur Barami and Chris Frith on decision making, collective decision making. And my lab in Haifa, we're working on social decision making. I'm currently spending a year in Princeton. And yeah, so far it's been very nice. These are many of the collaborators. Some of their names will appear, but I'm going to focus mostly. So I'm going to focus mostly on work that I did with Uri and Raphael and Joel and Marco. So in my lab, I'm interested broadly in the way people make decisions and behave in an interactive and dynamic environment. And the main idea here is that we have this kind of physical environmental settings, which include kind of physical settings where we work, where we operate. We have a social environment, like things like identity and groups and stuff like this, friends, and we have people interacting with them. So these are kind of cognitive agents. This could be like humans or AI, but mostly humans, that they are like way perceiving the world, and they make decisions and act upon the world. And they're not alone in the world. There are other multiple agents around them. So this kind of dynamic interaction may change the way the environment, change the social environment or the physical environment. And then this will, again, like new affordances, you change the way we behave. This is what I'm trying to tackle in a lot of different ways from very different directions. So I'll start by just like outlining some of the things that we are interested in. A lot of the work in my lab has been focused on advice giving and information sharing. So this is something that we are doing a lot of work on. And we're looking at the way people, so kind of the motivations underlying information sharing, specifically in the context of advice giving. And we were, for example, things like how accurate we want to be. So just being like very accurate or providing the best information we can get. Or using information sharing as a way to gain social status and influence. So this is another motivation. We also look at social risk avoidance, so people with social anxiety that perceive information sharing as a way to actually, it's a risky kind of procedure, so maybe they want to adjust the way they behave. And we show, for example, how these different motivations kind of have different weights and affect the way people share information in different contexts. So first we're looking at kind of contextual changes, so how changing the consequence of advice change the way that advice policy, and how individual differences may also change the way people share information. We also look at the way people learn from information, from advice, compared to social learning from observation, and looking at, for example, things like systemic trust and intentionality as a very important aspects of learning from advice compared to learning from observation. So we have a number of nice works and a lot of things working on this. In this context, we're also interested in the way people learn from or get advice from algorithms. This is again like something like, and we try to compare this mechanism to learning advice, like advising from humans. So looking at again, like what are the affordances, what are the assumptions people have, what are the motivations, how it changes the way social learning from algorithms compared to humans. So this is one big stuff of what we do. Another thing that we do in the lab is looking at empathy and specifically trying to think about empathy or empathic interaction as a dynamic interaction and learning experiences. So we have like an interaction, and then we can, it's not a one-off interaction. We just may interact over and over, and we're trying to use kind of computational learning models in order to model these empathic behaviors. We have a number of like some theoretical predictions, a number of already experimental settings showing that people kind of trying to understand what types of information in social interactions people are sensitive to, like what dimensions they're sensitive to, and how it shapes the way they adapt their empathic responses and provide empathic responses in the future. This is a work with So this is a work with Simon Shamanzuri and Lena, PhD student in the lab. Exciting. Another direction is related to this kind of cultural evolution direction that I'm interested in as well. This is a collaboration with researchers from archaeology, looking at kind of trying to look at archaeologic finding, especially like this is about 400,000 years ago, and looking at the emergence of social learning and groups. So this is the time where we have first kind of archaeological evidence that people started living in bigger groups. So these are, instead of just like 4 or 5 people wandering around, these are kind of 15 people living in the cave at the same time. So this is the groups that we're discussing. And we're trying to think about, first of all, modeling what is kind of enables, how it may lead to the emergence of kind of common framework, which would call kind of culture, but also, and also looking at kind of experiments. So this is, so what we have on the top is new experiments with participants learning to map hand access. Yes, this is a lot of fun for me, and it's a really cool collaboration. We do some work on kind of, this is a collaboration with people from political psychology, looking at moral injury and other. So this is kind of what is the, trying to understand the cognitive basis of moral injury, how it differs from post-traumatic disorder, and especially looking at how it relates to political participation. So this is, this is a really like interdisciplinary project. Again, like these are a lot of very smart, interesting people. I'm kind of the more kind of thinking about tasks and stuff like this. So this is a nice collaboration. And yeah, so and we also do like very more kind of standard decision-making and learning experiments. This is the one looking at the emotional representation compared to semantic representation. We also look at kind of computational psychiatry experiments, looking at the effect of stress on learning and adaptation. This is a collaboration with Uri Hertz, who's working on stress, and Norman Guy, who's working on it. So this is the cloud of things. So the kind of main thing there is learning and decision making, and applying it to different kind of questions. And it's pretty varied. So this is it. You're welcome to kind of chat with me about any of these. And what I want to discuss today is this kind of projects that trying to take this perspective and trying to understand things like social norms, collective behavior, like social norms and intergroup biases from a more kind of cognitive learning perspective. And I'll discuss 2 papers that are already out, and 1 paper that is constantly being rejected. And maybe I'll introduce some, if we have time, some new ideas. These are really recent things that I just have like pilot data, but I'll be very happy to hear your thought about this selection. So going back to this image, I'm interested in the way kind of people interact with the physical and social environment. And we know that physical settings in which people operate have different affordances, which are like, they allow different types of behavior to emerge. So this will shape the way, shape what we do, because this, like there are so many things that we can do. And we know, for example, that if you look at the kind of common goods problem or collaboration in kind of fisheries where fishes are under the sea, you cannot see them. It's a different problem compared to looking at things like herding. or kind of common grounds in herding, looking at agriculture, all of them kind of which are agriculture is very like things are we cannot take them and move them from place to place. All of them have like these kind of physical affordances that kind of shape what we actually can do. So what we see, what we can do. And we also have different places where we have different social settings. So these are different places where we can learn from each other, see each other, interact. Interactions are different in different places. So we know, for example, we see a lot of people when we commute, but we don't spend like a sort of quality kind of social time with them. So we cannot learn very sophisticated skills. We can learn about fashion, maybe, and kind of what to read or what to get drinks. But we also meet people kind of in coffee shops, in playgrounds, in work. All of them are places where maybe we have more meaningful interactions. And again, like where we are and what we see is something important. And even if we look really focus on kind of very small, kind of zooming in on behavior, we have different types of way people behave are sometimes easier or harder for us to interpret or to kind of perceive. So this is, for example, if sometimes people actively do things around us, so someone is littering or someone is collecting the garbage, and this is like very easy to detect and see that this is something people do around here. But sometimes we don't see it, we have to infer from observation. So for example, if we go to the kitchen area, we can see that the sink is full of cups. We know that someone actually put them, and it's kind of this is the norm here is not to clean your mugs, or we can think something about the collaboration, like a cooperation in this environment, or if we can see like that it's perfectly clean, maybe we can infer that everyone are kind of putting their work and that they're cleaning it. But there are other things maybe going on. So we know that, for example, inference compared to like actively seeing something actually going on are two different cognitive processes and demand different types of kind of mental effort. So this is already telling us that kind of what we see or the way we see it and the cognitive processes that needed to be to kind of infer what's going on are going to be different, and this may shape like how we learn about other things as well. So in order to understand how all these kind of things shape the way we human behave or collective behavior, we need to kind of take into account a lot of different kind of factors, and this is very challenging. And so far, one of the main kind of directions that people took in the literature was to try to really kind of summarize a lot of cooperative challenges in a very concise way in these types of matrices. So this is the prisoner dilemma, right? We all know this game. And we all know this perspective. So this is a very popular and useful perspective. It's been used to, it's essentially abstracts away a lot of the different kind of features that may be distracting for us and kind of say, well, look, this is the cooperative problem or the decision problem that we want to analyze. And now we can use tools like formal game theory solutions, but also we can use evolutionary game theory in order to understand what are going to be the stable solutions to this cooperative problem, how can we change them, what are going to be the dynamics, and stuff like this. And this, importantly, we can also run experiments in the lab using these kind of matrices, right? So we can, this is a very concise way to give like a lot of participants in different places around the world some kind of a task and ask them to see if they're going to cooperate or not, how much they're going to contribute, or and stuff like this. And then we can analyze it and compare it to benchmarks from the theory and compare between labs relatively easily. This has been very successful. However, it may be abstracting a bit too much. So because it doesn't allow us to have like a very complex, like it doesn't really care about what it means to cooperate. It just said, I'm going to cooperate or not, how much you're going to cooperate. And it kind of, all these kind of cognitive features that I tried to study before is going to. So in this work, this is with Joel Labo and Rafael Kosser from DeepMind and Marco Jansen from Arizona, who's working on sustainability. We're trying to kind of promote the idea of that we can try different experimental approaches to kind of augment this very concise description and try to make it a little bit richer, but still tractable. So this is the cleanup game. So you know the cleanup game? Yeah, so I'll just go over it quickly. So the cleanup game is what we're trying to suggest is using this kind of game. So the cleanup game is you have orchard of apples on one side, and you have dirt accumulating in the river on the other side. If you clean the more dirt you have in the river, the less apples you're going to have in the orchard. So you need to clean the river from time to time and then collect the apples. If you just eat the apples and not clean at all, the apples will disappear, there will be no more apples. And if you have one single participant playing this game, essentially what they're going to do is clean, eat, clean, eat. And sometimes you clean for a long time and then you eat all the new apples that emerge and then you eat. But if you have two or more players, now you can clean and there are apples emerging on the other side, and the other person can start eating the apples, right? So you have to kind of trust them to not eat in order for you to eat. So one solution is that you each have like.
Can you communicate with them, or you're just seeing them move around on the thing?
So it depends on the game. So in the settings, you can either have like communication, or you can just have like moving around the screen. So this is my approach is usually to let them move around the screen.
Yeah.
And you can see that like one kind of behavior is that each person is like a territorial kind of dividing the space between two of us. So I'm moving back and forth, and the other one moves back and forth. This is very stable because I don't need to trust anyone, but it's not very efficient because moving around taking a lot of time. So the other one is that I'm going to clean, and the other person is going to eat, and then we're going to switch places. And we also can move together, which is another strategy. So they're all different strategies, and all of them are cooperative strategies, but they're different. So this already shows us that moving to these kind of games is moving away from this cooperate or defect kind of binary situation where you can cooperate in different ways. We can now think about cultural differences and other things as well in this podcast. So this is a bit richer. And also it includes the problem, for example, if you have more than one player, more than two, like you have 4 or 6 players, you increase the likelihood of free riding. So someone who's just like getting harder to track who is eating, who is cleaning, who is contributing. So these are all very interesting kind of, we have a lot of interesting cognitive dimensions that we can study and see like what are the solutions that people and groups kind of find out in order to tackle this.
And Uri, what was that game called?
So this is cleanup.
Cleanup game.
Yeah.
I thought I heard of it, but I.
So I'm kind of, this is a new experiment that I'm planning to run with participants, but essentially this is being used by Rafael. So we've been used with reinforcement learning, multi-agent reinforcement learning models. And these are the kind of, so we compare a bit human and algorithms strategies. In Marco's work, I think that usually people kind of are allowed to interact. So this, like Marco Jansen was doing a lot of these kind of studies. I know Ostrom as well, this contact box. So these are the kind of approaches. Over there, actually communication is really useful. So what they're doing right now is we're tagging language models and trying to see what's going to happen.
Is the decision matrix the same as like your standard prisoner's dilemma, or is it a little bit different?
The decision,
Like how, like the rewards, it is a little bit different because prisoner's dilemma
yeah.
is about avoidance, and this is about games.
Yeah. So it's essentially very similar. Like if you were trying to kind of capture it, like the essence of it would be this will be like free riding compared to like clean compared to eat, free riding and so on. So this is relatively similar, but when you move to these directions. And what we're trying to say is that using these kind of games is a way to like it's a nice new tool for us to have, right? So we can think about like as experimenters, researchers, we can change the environmental settings, like changing like reward observability or location. We can change the actions that agents can have. So we have the freedom to shape the environment in a way that we want. We can also include things like kind of cognitive aspects to it. So how like things like memory, we can add these kind of aids showing things like reputation, how much contributed. We can change like the cognitive constraints by changing the size of the map and stuff like this. And we can also change the motivations and costs. So we can include things like we can just change the way we pay participants in this game. So paying them for individual or collective behavior. But we can also change social incentives by adding kind of social settings into it. So these are the kind of things that we can do, and then we can, what we suggest in the paper is that we can go in two different directions, or essentially we can go in both directions. One of them is using this kind of these games as a basis for multi-agent simulation. So this is the new kind of neural network agents that multi-agent reinforcement learning. They all operate in the same, so they all have access to the pixels on the screen, and essentially they learn turn by turn. They all learn together what is the best kind of policy to work on, or what is the essentially they face a screen. They assign some value to the screen, and then they can calculate what will be which action will lead them to what we call a big new state. And then they adapt their policy, and essentially after a while they kind of learn this very interesting emergent behavior. For example, different conventions, collaborations, quite a lot of. So we discuss a lot about the kind of things that you can get out of a very simple settings. But we can also go in the other direction. This is most of the stuff that I'm doing, is using humans to play these games, and then using behavior and formal cognitive models in order to understand what's going on there. Trying to because you have like a very nice control over the environment, but also you can track behavior and decision. So we suggest that this is an interesting direction to go, and I'll try to I'll discuss two projects that are going in the human part direction. And we have ideas about that.
Before you get into the real study, so there are apparently two ways. One is using like simulated agents to train reinforcement learning, and the other is to use human data to train reinforcement learning.
So what we're doing is that we can have like just humans playing this game, because this is something, now we have this kind of, we can test different hypotheses about the cognitive challenges and what kind of behavior is going to be emerging. And we can, because these games are, we can build them in a specific way. We can then look at, for example, try to use cognitive models that we build in the lab and try to feed the model to the data and see whether people, what kind of information they're sensitive to, what kind of biases they have, stuff like this.
Right. So theoretically, if the kind of the parameters you recover from human data matches with the reinforcement learning you learn, it's kind of a suggestion that the process are converged.
So there are two ways. One of them is if what we see in human behavior is matching what the simulated data is showing, we can see that they are working the same way.
Yeah.
Another interesting direction is that if you kind of identify some kind of cognitive bias in humans or motivation or something like this that shape the human behavior, you can then use it to augment the reinforcement learning model in order to add cognitive things like adding motivation, reputation, and stuff like this. So you can use it to inspire the solutions, but you can also use the simulation to inspire kind of solutions in human ways, because simulations are much easier to carry than kind of. So we think that really you can gain by doing both of them at the same time. So the first project that I'll discuss, the experimental project, is going to be about social norms. And I really like this definition by Edna Ullman-Margalit. Social norms are the unwritten rules that prescribe and guide behavior within a society with which most group members generally comply. And the reason that I really like this definition is because it's very operationalized. It tells something about what most people, most of the time, are doing, and it means that there is something, like behavior. We are able to observe this behavior in social settings. And we know that social norms can vary greatly between societies. So these are kind of very local solutions. So this is the norm about staying in, waiting in line or queuing. This is again from my experience moving from Israel to the UK. So this is on the left, we see an Israeli way to queue, which is very competitive and messy. And we have, this is the UK version where people are queuing up for, this is in Hampstead, sorry. Queuing up for the same kind of, same kind of scenario, but very different solutions. And if you kind of break the rule in each of them, you're going to be scolded. If you're waiting too much and you're not moving, like you're not competitive enough, people will be angry with you for why you're stuck there, staying waiting your time. And if you are breaking the line here, you will get scolded. So we tried it. Well, this is how we learn. But we also know that things can change with time. So, for example, during COVID, Israelis learned to stand in line as well. And we can see here, this is a different context. So in UK pubs, the line is actually very similar to what we see in Israel. So this is the very, people know that this is the different settings. And actually it's interesting because it seems that things are shifting in the pubs as well. So queuing up in pubs is now something that people are doing. So this is, I don't know, from The Guardian from April. So this is like 2 weeks ago about this new queuing up in pubs. So these kind of norms change between societies, but also within society over time. And this means that they are this dynamic process, which kind of we constantly have to kind of learn and update and adapt. And the theoretical framework for this project was the idea that, or not theoretical, but kind of the idea here is that in a society we have some kind of social norm that can prescribe a behavior, and this is the kind of behavior for the group members. And if we are a newcomer or anyone else, we can observe the behavior that everyone are performing, and then we can infer what is the rule and how to guide our interactions within this group. And we can learn it in 2 different ways. One of them is this individual way. So this is the one on the bottom. So we can just track individuals in the society and say, this guy is doing this guy is doing this. When I meet them, I'm going to interact in this way, but this does not inform me about new people in the group. So I don't know about individuals. I don't know if there's a new person. I don't know how to deal with that. We can also learn in a group level way. So we can look at different individuals and then we can infer this is what everyone are doing, and this can guide our behavior for other group members. So these are the 2 different ways to learn in the society environment. And in this project, I was also interested in this kind of how this specific behavioral manifestation shape the way we learn. So we know from reinforcement learning literature that people and animals can change or adapt their behavior responding to different punishments and rewards. Right? And punishments could be like things like active punishment, like active harm, but also the omission of reward. So I got the reward, but get it. And we know that positive reinforcer could be actively rewarding or the omission of punishment. So there was supposed to be an air pass to the eye, but didn't get it. It's a positive reinforcer. And we also know that animals and humans respond differently to positive and negative reinforcer, but they also respond differently to active and omission action, active and passive behaviors. So this is something that we already kind of know, and I was wondering if I can take this distinction and see how it shapes. So this is very low level kind of learning mechanism, and see how it shapes things like learning about social norms and how to do it. So I use this game. So this is a different game. This is the Star Harvest game. It's in this game we have 4 players. They're moving around the screen. There are stars emerging, and they can collect the stars and get stars. But they can also zap each other. So you can zap someone by sending this ray. So instead of moving, this turn you actually zap someone. You send a ray, and everyone affected by the ray, everyone caught in this ray are going to be affected by it. And this is a game, again, they use with multi-agent reinforcement learning. I thought, well, let's use it with humans and see what they do. In this game, we have one, so in the experiment, specific experiment, we have 1 participant. This is this P person, and the other players are played by algorithms, by bots. And the algorithms can be zappers or avoiders. So zappers are algorithms that from time to time they will zap. I'll tell you a bit more. And the avoiders are bots that never zap. So they just move around and collect stars. And participants play 2 types of games in 2 different groups. One of them is the negative zap, and the other one is the positive zap. In the negative zap game, when you zap someone, they get out of the game for 3 turns, and then they come back. In the positive zap game, when you zap someone, you send them a small star, like a token of star. It doesn't cost you anything, it just costs you the time, but instead of moving, you send them a star. So here's the positive and negative things. And again, the other players could be zappers or avoiders. So avoiders, they don't zap. The zappers they zap. In the negative one, if someone is on their path to a star, they zap them and get them away. And in the positive one, they just have this likelihood of zapping other players around. And this kind of maps nicely into this 2x2 design I showed before. So in the negative environment, zappers are showing actively harming behavior or competitive behavior. The avoiders are essentially harm omission. They could zap you, but they didn't. And in the positive one, we have the benefit action. Someone actively send you a star or sending people stars. And people could send them a star, but they didn't send them a star. So this will be the benefit omission. And I was wondering how people respond to these different kind of contingencies and especially what happened over time. So this is just a demonstration of how this thing looks like. Yeah. So participants play this game in the online. You can see them moving about. Here, I'm the blue guy. I've been zapped. And I'm out. Yeah. And the red one zapped the green one. Again.
How do you see the zapping? Is that when it goes red across?
Yeah. So essentially, it's emerging from the specific player.
It's like a laser shooting down a row. Okay.
And everyone else. So this was just like a couple of like 1 minute, but so they played this game for. So as you saw, it's you have this kind of traffic lighting. You have that turn by turn, so it's not that people constantly moving. A participant played this game for 75 turns, and then they moved to another game. It was also always kind of, if they started with positive, they stayed in positive, they started with negative, but they have different kind of colors. That was how you're switching with different players. They have different colors, and essentially what happened is that they moved from environment where participants were zappers to participant avoiders or vice versa. So they always started with avoiders to zappers, zappers to avoiders. These are the 4 experimental conditions. We never switched from positive to negative behavior because it's just in what to do. And we're interested here in where are people going to adapt their behavior to what other players around them are doing in the first time. So initially, what are they going to do? And then what happens when they move environment? Are they going to shift and learn new things, or are they going to just keep on doing whatever they've done first? So this is, okay, good. So this is the main result of this experiment. So the behavioral result that we have is that we see always like the left bar is the first block. And we can see that in the first block, participants adapted their behavior to the behavior of the ball pairs around them. And when they were interacting with zappers, they zapped. When they were interacting with avoiders, they tended to zap less. This is both in the positive and in the negative. And the interesting thing, so this is the number ones everywhere. However, the interesting thing is what happened when you move to the new environment, and we can see that in most cases people adapt their behavior, but there is one case when they don't adapt their behavior. So when they start off, but when they start off is the leftmost side, when they start with avoiders and move to zappers, they always increase the zapping behavior. So we can see it both in the positive and in the negative cases. But when they start in the zapping condition and moving to the avoidance condition, they adapt in the positive one, and they don't adapt in the negative one. So they start with active harm condition. So people are zapping each other and getting them out of the game. And then they move to a new environment where new players, they never zap, but they keep on zapping as if they are in this first condition. So this is just, this block over here. So they start in the active harm, they move to the passive where nobody is actually zapping, but they keep on zapping. The zapping rates remain the same. And this is, for example, here we can see that they can actually reduce the zapping behavior. So they move from the environment where people are zappers to environment where people are avoiders. Importantly, in this case, avoiding the zaps is actually like benefit omission. In this case, this is harm omission. So this is 2 different things. This is the positive reinforcement.
Is the zapping behavior, like, is that more beneficial for like earnings and behaviors?
So
does it mean like they actually learn like the best strategy, even though it's like
So it doesn't change, so it depends, so first of all, the number of stars I actually get in the end is not that different between conditions, so it's not that this is the optimal way, actually there are two different ways. The best way to work when everybody are avoiders is actually to everyone kind of harvest their own part of the screen. So because stars are emerging randomly in different places, so actually it's best if I'm staying here, you're staying here, and we're not getting each other. It is better when the people are zappers to zap, because then because they're likely to zap you as well, because they are a bit more competitive, and there so you may want to preemptively zap them or wait for the sake. So it's not strictly like one, like there's no strict mapping between how many stars you get and start you choose. This is obviously also the case. The zapping with the small stars, and the small stars actually like we just send them tokens. So the next step in this experiment was to try to use computational reinforcement learning or learning models to kind of capture what maybe kind of asymmetries in the way people learn about this stuff. So we used our models essentially look at what happened when we observe someone. So essentially, the idea is that you observe some behavior, you update your belief about the likelihood of this player to zap, and then it may affect your decision in future interactions. And what we try to model is these decisions. So we fit the model to the decisions that the participants actually made. And we just try to understand how people update their beliefs about other players' behavior. So the individual level model assumes that when I see like Mr. Brown zapping, I'm going to update my belief only about Mr. Brown, and this should not affect that much my decisions regarding Mr. Red. The group model essentially assumes that I update everything in the same way. So when I see Mr. Brown zapping, the likelihood of everyone is increasing in the same way, and this should affect my decision about Mr. Red. And this biased attribution model or a hybrid model essentially says that when I see Mr. Brown zapping, I update my beliefs about this person, but I also update my belief about the other group members, but I could update in slightly different ways. So it adds some flexibility to the model, and it means that like this goes up by 1 and this can go up by 0.5 or something like this. Okay. And also we have different learning rates for active and passive behaviors. So essentially our models, we don't specify what it's going to be. It could be that they're the same, but we allow some flexibility there. And we can say you can learn differently from zaps and from avoidances. For example, zaps like you update a lot, and avoidances you update a little. So you need to see quite a lot of avoidances to overcome one observation of zap. So this is the learning model. We have this learning rates, and we have how much we generalize to other players. And we also have a decision. So this is just the equations, essentially saying what I just said you. And after you observe them, we have the decision process. So the decision, when I just see this person, is going to be affected by a number of parameters. One of them is how close I am to a star. So this is kind of, if I'm very close to a star, I'm probably going to go for the star. How close I am to the target. So if they are very close by or not. And my belief, so what I learned so far about the likelihood of the target to zap. Okay, so if I learned that this target is a zapper, I'm more likely to zap them. So this is the decision process. And now we feed the model to the data, to the behavior of participants, and we can look at the different parameters. So what we see here are the learning rates. So this is for the zapping and for avoidances. And we can see that in the negative condition, where you zap someone and they get out of the game, learning rates for zaps are, so in both cases, learning rates for zaps are higher than learning rates for avoidances. So this means that for any observation of zap, you increase it a lot, but then you need to see a lot of avoidances in order to overcome it or this one zap observation. So there's this bias towards zapping or positive or active behaviors. And this is the group level kind of generalization. So here what we see, if it's greater than 0.5, it means that you are, the higher it is, the closer it is to 1, the more you learn from one individual, you generalize to all other group members. So for 0.5, it means no generalization in small. And what we can see is that in these two cases, we have greater group level attribution, which means that we observe one person, but we also update our beliefs about all other group members. And in these cases, we don't see that much. So essentially, we observe one behavior and we don't attribute it to other group members. So we learn only about individuals. And these two bars are the negative reinforcers. So this is the benefit, omission, and harm action. So these are the cases where we generalize to other group members. And these two bars are actually the positive reinforcer, where we get like a reward or the omission of punishment. And in these cases, we mostly learn about a specific individual that we interact with. So what it means that zapping active behaviors are learned more quickly, so they have more impact on our impressions. And it also means that negative behaviors are more likely to be generalized to other group members. If you're generalizing stuff to other group members, it means that you don't need that many observations. So one observation is enough to update everything, right? And if you're learning an individual level, you need to like have a lot of different individual experiences. And this shows that actually this red one benefits from both of them. It's both active and harmful. Like the active harmful behavior is much like is essentially you don't need a lot of information like you learn about it very quickly, and it's taking very long time to kind of erase this impression. No, I don't have it. I think I hid the slide. But essentially, if you look at the simulation, what you can see that people learn very quickly, and then they kind of, it takes a very long time for them to erase this impression of like this previous experience. And this can explain what you see here in this lack of adaptation, where the previous experience kind of just keeps on affecting your behavior in this new environment. It takes a very long time to overcome. And I think the main point here is that the behavioral affordances and kind of the cognitive demands that are associated with them shape the way we learn about these social norms, and they can also like previous interactions shape our future interactions, our experiences kind of keep on going. So it means if you move from one environment to the other, it's not a symmetrical move, things are carried on from one environment to the other, and you need to kind of maybe think about how to make norms more active or more apparent, more clear, easier to capture, in order to make sure that people are switching accordingly and then interact with it. So essentially what it shows is that these kind of cognitive constraints can like higher level effects and shape the way we learn about social norms and behave socially. So this is project one.
Your question. So like in terms of social norm, like in classical social norm literature, you have like descriptive norm and injective norms. But in this study, see, I'm just trying to wrap around which one it is, because like the kind of that behavior seems like a punishment, so that makes a norm more injective rather than like you're descriptively just observing what others are doing. So
yeah. So I think that in this case it's not exactly punishment. So it's a competitive. It's the action itself. So you're not punishing someone for doing something. You're just zapping. This is the way you play the game. Right. So I think it's more in line with the descriptive norm. So you just look at the kind of statistical, distribution of what people are doing around you. Right. And what we're trying to look here is essentially how you kind of, from a sparse observation, how you come up with this distribution and how you kind of generalize it to different people.
Yeah, but I couldn't imagine a participant who's like being zapped there, like, I just don't like this person, I'm gonna zap you. Like, yeah. I'm not trying to get the stars, you heard me, so I'm just. But
the question is how likely you are to also zap other players as well. So you say, well, someone zapped me, I'm going to zap everyone else. Right. So this is essentially what we're trying to look at. So for example, and especially how long it's going to take. So if I experience one zap or a number of zaps in one environment, how am I going to interact with new players in new environments? And essentially what we show is exactly what you said. After one zap, I realized I did have zappers. And it takes me a very long time to overcome this kind of biased zappers. Yeah. And I think it's a good question of, in other projects, we are trying to look at punishment. Here, I think, even though we call them punishments and rewards, these are essentially like aversive and appetitive relationships. It's not exactly not punished by, so nobody's trying to shape your behavior. Cool. So, I don't know how much time do we have? Fine.
We have another 30 minutes.
Okay. So I'm not sure. Yeah, so the next project was essentially building up on this experiment and trying to look what happened when we add group identity or social markings of like groups into this game, and whether people learn differently when they have this kind of know about the group identity of the players. And we know that people are sensitive to these markings. We know about intergroup bias. You all know about interactions and bias. I don't need to tell you about these things, but essentially what we're trying to do is to use our paradigm in order to see how this kind of in-group, out-group identity shape the way we update we learn about what other people are doing, about our beliefs, and whether how it's going to be affecting our behavior, whether we can actually overcome, if we have people from different groups behaving the same way, is going to be, we can overcome the social identity signals, or it's going to linger. And essentially what we see is that there is a strong persistence of this intergroup bias. And we're trying to understand what is going on. So we carried the same experiment, the same game. Now it's only in the negative domain because it became complicated enough. We can focus only on one experiment, one game, that game. And in the beginning of the game, we just had a minimal group manipulation where participants essentially told them, please choose a color for your team, for your avatar. You can choose from the oranges or the blues. We have another version with green and purple. And then you play the game with 4 other players. The players are, 2 of them have the same avatar color as you, and 2 of them have the other color. So these are the outgroup and the in-group. And this is the main manipulation that we had. And we had participants playing different conditions. So we had, this is the neutral condition. So they always played only one block now, either in the grouping or the neutral condition, where you play with different groups. And the players in the game were either all zappers or all avoiders. So they all presenting, this is exactly like we had before. Or we had a mixture when 2 of them are avoiders, 2 of them are zappers. So one in group is a zapper, one is an avoider, one out group is a zapper. So the behavior of all players were also always the same in a sense. So the group identity shouldn't play a super important role. Yeah, and you play this game for 100 tries. So you have quite a lot of experience with these participants. And essentially, we were interested in how this group identity is going to be affecting 3 different mechanisms. One of them is this prior. Essentially, we're just more likely to zap players that have different colors from us, from the setup that we just from the start. So this is it's likely to zap me. I'm just going to zap them more. We were also interested in learning. So this is changing the learning rate. So for example, for outgroups, I may say that after I observe them zapping once, I can increase the likelihood of them zapping very much. So my beliefs will change a lot. And for in-groups, maybe I won't change them that much. I'll say, well, this is a one-off or something. And finally, we were looking at attribution. So for example, what happens about my beliefs about this small guy over here when I see a blue guy zapping. So if someone from the outgroup is zapping, is it going to change a lot my behavior, my belief about other outgroups? And for in-groups, maybe not. So these are the 3 components, and we already kind of discussed these components in the modeling side. So we had a model, we had the experiment, and now we have everything we need, right? So now we just need data. So this is the results. So these are the results for the homogeneous conditions. So these are participant with players that were always either none of them was zapping or all of them were zappers. Okay, and what we can see here, this is the learning curve. So this is essentially when we beam the blocks to different, we beam the experiment to different blocks. We can see what's going on over time. This is the average over the entire block. Light colors are the avoiders, the dark colors are the zappers, and we can see that participants essentially when they always show this intergroup bias. So they always zap outgroup players more. So this is very strong. These are the light colors show you that even when they don't see any zapping of behavior whatsoever, they zap the outgroups a lot, much more than, and in groups they almost don't zap at all. even though the in-groups and the out-groups behave exactly the same, they zap each other and they have to zap their own groups as well. And this is the neutral condition, which is somewhere in between. So in two participants, so this shows you that this is really kind of going away from the middle within these arguments. What we see also is that participants can learn over time. So even when they play the game with zappers, they increase the likelihood to zap over time, but they still show at the end a big intergroup bias. So they increase it, but they zap outgroup more than in-group. So it's not doesn't mean that they learn and overcome their initial biases.
So quick question, so is the only manipulation just the color? Do you give them any information, like this is like a dip, like, or is it just the color that's the?
It's just the color. So we tell them to pick. So it should be said that in this context of video games, the colors is a very strong kind of marker, because people are used to, you know, whenever you play any game, like an online game, people with different colors are different teams. We all like immediately have these assumptions.
Yeah, but that's still pretty subtle manipulation, so impressive.
Yeah.
Effect.
No, it was, we were very surprised that it's so strong.
Yeah.
And I'm just replicating it now, and I'm trying to introduce other manipulations maybe I'll show again. This is still like so strong.
Yeah.
And it's very hard to shift it. And this is the mixed condition. So in this case, they played with one player was zapper and the other one was avoider. So these are all kind of in the same game. And we can see that participants differentiate between players based on their behavior, but also based on their group identity. So they realize that this is a zapper and this is an avoider, the zappers, the avoiders and the zappers. They learn about it over time, but we can see that, first of all, there's still a difference, but we also can see that, for example, this distinction, which is very clear over here, is not that clear over here. So they become slightly more similar to each other. Here, it's also the case, but they already started pretty similar as well. Okay. So it shows us that there may be some kind of attribution going on there. So this is the main behavior that we can see here, and you see that even though they learn over time, even though they can learn, even though they can differentiate, we still see this very strong persistent output bias. And then so we have another behavioral measure here, which is at the end of the game, participants could have 10 extra stars that they could allocate to the different players. So we can see that they always give more stars to the in-group compared to the out-group. So we can see that, and the neutral one are essentially at 2.5, which means they, on average, gave everyone the same number of stars. And in the mixed condition, they give more stars to the in-group avoiders than to the in-group zapper. They always give more to the in-group compared to the out-group, but they don't differentiate between the out-groups. So essentially, regardless of what they experienced before, they essentially say these are all out-groups that give them mess. So this kind of shows us from like another measure showing that there is this kind of learning effect. They can acknowledge and learn about the behavior of participants, shapes their behavior toward them, but also that they kind of treat them slightly differently, their in-group and out-group based on their behavior. And I think that this kind of effect that you treat outgroups in a similar way, even though they behave differently, you kind of learn about it, is very interesting. So now we fitted the models, we just expanded them a bit in order to include different learning rates and attribution rates for in-groups and in-group and out-group. So we have now zap, avoid, in-group, out-group, so a lot of different parameters instead of that. So we get a lot of different players. And we also moved a bit, we made the prior is outside, and we have the bias, the prior, and decision is dependent also on this, how close you are to the star, how close you are to the target, and how many targets to set. And we fitted this model. It was the best fitting model, which was good. And now we can look at the parameters. So what we found here is, so this is, let's unpack it a bit from left to right. So we can see that the priors, which is how likely you are to, like overall bias to zap, are much higher for outgroup compared to in-group, and also compared, this is the overall bias. So participants were just more likely to zap outgroups compared to in-groups. In addition, so this is what this says, and this kind of makes sense. Now we look at the learning rates. So we see that again, these are the zapping and the avoidances. You can see that zapping learning rates are much higher than avoidances learning rates. So again, like what we saw before, when you see someone zap, increase the belief, you need to see a lot of avoidances to decrease. But we can also see that the likelihood of zapping, that learning rate for zappers, for outgroup zappers, is higher than for in-group zappers, means that you really just, for one observation of zapper, you increase it almost immediately, and we'll show it a bit later. And in the attribution rate, we found something that was a bit counter, we didn't really expect it. It's so the first, we expected that there will be a complete attribution for outgroup and no attribution for in-group. So this was my belief when I started this experiment. What we found was something different. What we found was that for in-groups, we see complete attribution. So the attribution level were very similar for zapping and for avoidances. So if you see someone avoiding, you attribute it to all others. If you see someone zapping, you attribute it to all others. It makes them much more similar to each other, these in-groups. For outgroups, what we see is that the attribution for zapping is very high. It's like very similar to what we see before, but attribution for avoidances is almost zero. So it means when we see someone zap, we assume that all other outgroups are zappers. But when we see someone avoiding, we say, well, this is just this person. There's nothing from this observation that tells me anything about the outgroup. And this is like this asymmetry had very strong effect on the beliefs. And we also see that they are affected by all the other parameters, the distance from star, the target, and the likelihood to set.
So is what you're describing basically the outgroup homogeneity?
So I thought, what we thought was that outgroup homogeneity would mean that we think that they're all the same. What we see is that outgroup the homogeneity effect is actually only on the zapping dimension and not on the positive dimension. So we think that they're all equally likely to similar zapping behavior, but we don't think that positive behaviors can be assigned to all outgroups.
So it's homogeneity for negative behaviors, basically.
Exactly. And this is like more classic homogeneity idea in the sense that they're all pretty much similar to each other. And we can look at we can evaluate like the learning curves from the model, and we can see that these are the homogeneous conditions. So when everybody are zappers or everybody are avoiders, we learn about zappers, we learn about avoiders because we don't have both information. But when we have a mixed environment, the zappers become, the estimation is going down, the estimation for avoiders going a bit higher. So this is in line with what we saw before. They're a bit more similar to each other. So they're both going back to the middle. For the outgroup, this is the homogeneous condition. First of all, it goes much higher than for the in-group. This is because of the higher learning rates. So we learned it quickly and the estimation is much higher. But when we look at the mixed condition, this one is not going down very much, but the avoider is going a bit higher. So the avoider is going up without the zapper going down. So it means that they're all there's just a shift towards more negative assumptions without this kind of collapsing to the middle.
With the avoidance, correct me if I'm wrong, it's an inaction, right?
Yeah.
So do participants consider that to be a true positive action, or would you consider, if you added a third action, let's say, where it's a straight positive reward, would you consider that to be an even stronger effect? Is that your estimation here?
Yeah, so in this case it's a bit harder because they are kind of mixed together.
Yeah, in this case.
I think that there is a number of ways to think about this avoidance behavior. So one of them is that avoidance is it's a bit harder to infer causal and intention from this behavior. So this is, I think, why we have this lower learning rates for avoidance in this case.
Yeah.
But it's definitely the case that it's a more positive thing,
Absolutely.
right? So if you see someone zapping and then they don't zap at all, you just decrease the likelihood of zapping. It's also important to understand that even though we have this kind of post question, like afterwards we show how they, we had a couple of other questions about like intentions and stuff like this, but essentially we have some information about the reporting what they believe. Here, what we see is how their beliefs only in relation to how much it affected their zapping behavior. This is a distinction that it's important to have in mind. It's clearly affecting their behavior, so it's important, but maybe they can have like other more kind of elaborate beliefs about in-groups and out-groups, what they want to do, why they did things, which we didn't like tackle directly. But what we look at here is how it these things affect their zapping behavior. And I think that this is the main thing here is, again, like we have different asymmetries in different levels. They all kind of contribute to this kind of more negative evaluation or beliefs about outgroup zapping. and they kind of resist the effect of actual observation, what we see. So in this case, if you have these kind of asymmetries in place, it doesn't matter what the players are actually doing, because you just update your beliefs in a different way. So even though they all behave in the same way, this is, again, like just the learning effects. If you just give them more, like the learning rates, more weight or asymmetric weight, the same kind of behavior can lead to very different beliefs about in-groups and out-groups. So social identity, if it really changes the way people kind of other their behavior, which is what we say, is kind of going against the actual behavior of players. So just being exposed to in-groups and out-groups behavior is not enough to overcome this from this very cognitive perspective. So this is essentially the final idea here is that yeah, we have this, the social identity shapes the way we update our beliefs and learn about other behavior, and this can work really to sustain and lead to the persistence of this intergroup bias, like just by the virtue of the way we learn and act. And the last bit of information I'll be happy to share. So this is a completely new project. Trying to, again, like building up from this, we thought that this would be an interesting, like again, like nice paradigm to play with, and trying to look at social categories a bit more, a bit of granular level. So trying to move from intergroup bias, where we have this clear in-group and out-group, to something about social categories. And this is something that I'm interested in because I think that humans, that in social settings, we have this tendency to, that the easiest way to categorize is to have this binary categorization. So we know classifiers in computer science, but also the way people look at people learn about categories in general. They're very easy to say, well, let's have a boundary, or let's have some kind of rule. Everything above this is A, everything below is B. These rules can be pretty elaborate, but this is like the easiest way to think about categorization. Whenever people whenever in the lab, people try to add some more rules, people are finding it very hard to implement. They move to either higher dimensional rules or they're just random. People are very good at switching from different contexts. So if you have one context, you can think about one rule, different context, you can think about different rules. But still, this kind of binary distinction is, I find, very interesting. So I think it's interesting from kind of more cognitive basis, and also very interesting in kind of social settings, especially when social settings could be very complex. People can belong to different categories, or things are actually on continuous dimensions. And this is, and it's not clear how we deal with this. We deal with it very poorly, and we assume that people are just like with us or. So this is really very preliminary. I'll describe the ideas and some data. So we have this work. Essentially, what I'm trying to think about is two different ways about paths to social categories we can track. One of them is this intersectionality idea, that people can belong to different categories at the same time, and adding multiple categories may lead people to either, to have this interaction effect where you treat someone special because they are now in two different categories. And the question is how much we take into account these multiple identities. The other direction is looking more at the continuous level, where there is a continuous of, like, let's say it could be social, or kind of this is a gender kind of continuum. And in this literature, we have this idea that actually people don't like the intermediate kind of people. So people that are not here nor there are treated differently than people that are in one category or the other. And this again shows that we really like this, playing the world in two different ways. There are a lot of interesting works on social categories from a lot of literature on this. But I think that there is likely less looking at kind of how it interacts with this more kind of cognitive basis. So we know it again in cognitive psychology. We have signal detection theory suggesting how we differentiate between things. Also kind of gives us predictions about continuous state dimensions. And we can also think about different, this is something that I like the kernel problems, where you can move to higher different dimensions, where it's easy to slide things to different, to move from an environment where the differentiation is like non-linear, to another space where it's actually linear, and then you can separate. And I think that this is actually an interesting, I don't know, exercise in thinking about how we can redefine the boundaries between social groups in higher dimensions. Yeah, I'll be happy to check once. But with all these ideas, what I thought will be interesting is to do the exact same game where you pick two different colors in the beginning, and then play it once with a group of players that change just gradually over time. So you play with your in group, which is exactly like you, is green. The out group is orange, but there are people in between. So how do you treat them? Are you going to actually differentiate between them? Are you going to how people are going to treat these new dimensions, this new variety? And also look at another effect where we have this intersectionality, where you pick a color, but you have people with similar colors, different colors, but also with different shapes. So now we have different information. So these are just like some theoretical predictions. What can happen? You can just treat everyone the same way, because once you have this dimensionality, essentially you don't need this in-group out-group distinction anymore. So you'll just treat everyone the same. You can have some kind of rule that separates them. So saying that in the middle, these guys are out-group, these guys are in-group. So collapsing back to a binary decision. And we can also have a continuous one where the more similar they are to you, the less likely you are to zap them. This is, I think, more cognitively demanding kind of thing, because you need to keep track of how similar they are to me. And we can also have this intersectional pattern where people just don't like people that are not here or there. So this is something essentially from, so this is one kind of, these are the kind of predictions here. And in the intersectional, we can think about like caring about color, caring about shape, caring about both of them, or really looking at interaction where you treat these guys very differently. There's also another prediction that you may, again, like have one boundary like the one we have here, sorry, but maybe you'll treat like just similar people are going to be treated differently than everyone else. So you just set a boundary, but in different ways. So these are the kind of different predictions. I think they're interesting enough to merit an experiment. These are really, this is 20 participants in a pilot study. So this is how they behave differently for in-group and out-group. We can see that we run the experiment in the all polite and all competitive one. In the all polite, we can see that participants showing the same in-group outgroup that they showed before very strongly. Where it's competitive, it's less pronounced. So it's interesting to think about what's going on there. But they do differentiate between them very clearly when you ask them to allocate stars at the end. So they fall into these in-group outgroup things. And this is the continuous one. We can see that in the continuous one, essentially the in-group outgroup is much less pronounced. So now, because there are no clear reds, oranges, and greens, essentially introducing diversity means that the in-out condition is kind of going away. So its impact is much lower. You still see it in the allocation. You see this continuous one in the all competitive one, but it's not this clear, I don't know, step function that we see over here. This is just like I said before, it's 20 participants, and just to see if we capture anything interesting, but I think it already shows us that there is differences between the way you introduce these social categories. If it's like multiple categories compared to a continuous dimension, and thinking about continuous dimensions compared to kind of binary categories is interesting, and what it means to a society to have continuous versus binary kind of thinking. And yeah, we still have a lot of work to do there, and I'll be very happy if you have any ideas about these kind of problems and kind of what would be a cool finding or what would be an interesting manipulation on top of what I just suggested. I'll be very happy to hear. And yeah, so that's it. I showed you a number of works trying to look at this, how we try to look at adding more complexities, either from cognitive perspective. We now have new work trying to shape the environment. Yeah, there are a lot of new directions that we're considering in like how people kind of change the affordances of the environment, building like mini cultures in the lab and seeing like how we can push people to converge to different types of solutions, and then trying to think how to implement it or how to translate it to real world implications. This is the kind of thing that I'm thinking about a lot these days. And yeah, so that's it.
Thank you, Uri. We only got about a few minutes, because then we're gonna go for taking for lunch, and we lose this room in about 2 or 3 minutes, so we have time for 1 or 2 quick questions.
That's really interesting. I was thinking a bit about the intergroup study and then with your like future directions. I know you find that sort of like classic in-group outgroup bias. Do you think that if people were to switch groups that they would hold on to that bias? Do you think it would flip, or do you think that you would find something similar to what you found in your like your pilot data, where when things are a bit more ambiguous, it kind of washes out?
It's a good question. So I think first of all, we asked them in the end if they want to switch groups. I don't remember what was, we asked a number of questions. This was something that Uri said, well, it'd be interesting to see if you could play the game again with the switch. Wouldn't they not want to switch it? I think that they just but they weren't that, it's not that they really liked their own group, but they thought it was pretty kind of symmetric situation. My prediction is that when you switch, you will see that it's going to be a flat line or something like this. However, it could be that I'm not sure. So it could be that they switch because the markings are so salient, the colors, that they can say, well, this is a new settings. I'm going to switch I can take my priors and I completely switch them around. This would be interesting to think. It's realistic if you will tell them you're not switching, we're mixing the groups. So, or something like this. So now you're playing with someone from the other group or something. I think that especially interesting will be one sort of parameters they will take with them, and some other parameters will change. So learning rates will be similar. So we will see them initially with bias and then overcoming it.
Okay. Any other questions? I guess okay.
I have a
Last
question. Yeah, sure. So on the continuous one, you seem to find there's no like this characterization effect, but something from like the traditional category and concept literature suggests like kind of the density have some context, right? Even if you think about the gender as a continuous, there are a lot of more people lying on the kind of some prototype learning. So I was thinking if in your experiment, if you add like density to some kind of color having more, you might be able to see the categorization effect.
So I wonder, so this is a good idea. I was thinking about like how many players you can add to them, and this would be really interesting to think about this. And again, like showing that changing from properly like binary distribution to gradually changing into a non-distributed.
Okay, I'm gonna end there, just because we want to take for lunch, so thank you.